So today I'm going to be talking about our active filters lab, and the first thing we're going to do is build two simple circuits, a low pass filter and then a high pass filter. We are going to look at these in a variety of ways. First we're going to look at its calculation, so a pen and paper. Next we are going to simulate it in LT Spice. Finally we are going to build the circuits and then examine how they behave. This is our calculation portion. Low pass filter is a filter that passes signals with a frequency lower than a certain cutoff frequency and attenuates signals with frequencies higher than the cutoff frequency. And a high pass filter is a filter that passes signals with a frequency higher than a certain cutoff frequency and attenuates signals with frequencies lower than the cutoff frequency. And then you can see that we have drawn here for a low pass filter and here for a high pass filter. Both are generally the same, so I'm going to try to keep it quick. But we use the voltage divider equation in both. And for a low pass filter, we found that H equals 1 over 1 plus j omega c. And for a high pass filter, we found that it's omega rc over the square root of 1 plus omega rc squared. We looked at the special cases to see what we could predict, and just going through the low pass filter, for instance, when omega goes to 0, we would expect that the output size equals the input size and that they are in phase. As omega goes to infinity, we would see that there's no output and it would lag by 90 degrees. And then finally, as omega approaches omega naught, and we know omega naught to be 1 over RC, that it would be 1 over the square root of 2, or 0.707, and then we'd expect its phase shift to be negative 45 degrees. For a high pass frequency, as omega goes to 0, we would expect the magnitude to go to omega, and then it would be in a phase shift of 90 degrees. Next, we would see that as omega goes to infinity, the magnitude would equal 1, so again our output size would equal our input size, and there would be no phase shift. And then finally, as omega goes to omega naught, we see the same situation, except that our phase shift is positive 45 degrees. Alright, so I constructed LT spices of a low pass filter and a high pass filter. If we take a look at the low pass filter and we run it, and compare it to our pen and paper, we see that at low frequencies, the input equals the output. At omega naught, which I calculated to be -3, a magnitude of -3, we would expect a phase shift of -45 degrees, as you can see over here. And then at high frequencies, we see that the phase shift goes to -90 degrees. And then after that omega, we see a drop of -20 decibels per decade. Next, if we go ahead and look at the high pass filter, we saw that at low frequencies, there was no output, and we would expect it to increase at 20 decibels per decade. And then again, that omega is going to occur at -3 decibels. And we would expect an opposite but equal phase shift of 45 degrees. And then at high frequencies, we see our phase shift go to 0, and that our magnitude is equal to our opposite of our output. So here's a picture of our setup. As you can see, we have a voltage going through a 1K resistor through our 1 microfarad capacitor and then to ground. We then connected our DAC system around the capacitor, as you can see.
If we press run, the phase shift should go from 0 to 90 degrees, while the amplitude goes from 1 to close to 0, and we have to let this run all the way through. We should get a circular, like this green line. The amplitude was 0.15, but that's because it can't measure 0 with the DAC assistant. Okay, so once we let it finish, the phase was at 90 degrees, which is what we wanted to get, and the amplitude, the difference was 0.1. The amplitude should have been 0, but the DAC assistant can't do 0, so